hashing functions, this time we do multiplication method. Yeah. So very simple. So here the purpose, let me recall the purpose. So for the division method, we need to choose m number, modular m number carefully. Yeah, because some m numbers, the performance very bad, and some m numbers, the performance much better. Yeah, yeah, but still not very convenient. Still a lot of problems. Yeah. All right. The reason, the division method reason, it does not perform well for most of the m numbers is it's hard to break the patterns. If your data has certain special patterns, then it won't perform well. Okay? So here you can see the key. When we design the hash function, the key is if your hash function is robust enough against most of the patterns. Yeah. So here, it's hard to describe the patterns. Just some special property, some rules, properties, patterns. Okay? Yeah. All right. Choose, so here, the multiplication method, the design. Yeah. So here, let's start the design. Yeah. First, we need to choose a special constant A in the range between 0 and 1. Yeah. Yeah. This A, you will see, we use this special A to help us break the patterns. Yeah. So you can imagine what kind of A can help us break the patterns. Yeah. All right. Then you have a hash key K. K is the hash key. Okay. But that K, you multiply this constant A, so you can get a larger number, right? Yeah, larger number. But we truncate the integer part. Mod 1, that means all the integer part are removed. All the, integer part. Greater than 0, integer part. Greater than equal to 1, all the integer part. We only keep the decimal part, fractional part after the decimal point. We only keep the, that part. Yeah. All right. So then multiply the number of slots. M is the number of slots, right? Yeah. So this M, that is the number of slots. So here you can see it could be any number. Okay? So we do not require, prime number or not. No, not necessary. Any number. Okay? So even 100. So if you have 100 slots, you just use 100. Okay? Yeah. All right. So then we use M to multiply that fractional number. Okay? Yeah. So that's simple. Then you take floor function. So this is the multiplication method. Okay? Yeah. So you can see, if you compare with the division method, so more convenient to use. Yeah. All right. So then, now A is important. Yeah. So when you choose this capital A, it is important. Yeah. All right. Yeah, so for the fractional part, so we know fraction part, here you can see, because we use M to multiply a number less than 1. The fractional part always less than 1, okay? So this M thing, M multiply a number less than 1, less than M, okay? Less than M, yeah. Then we take floor function, the greatest number is M minus 1. Okay, n minus 1. The number of slots, the slot number from 0, 1, 2, n minus 1. Okay, yeah. All right, so you can see that function give us the value for the slot numbers, these M slot numbers. Okay, all right. Yeah. A good selection of capital A can break most patterns. So what do you treat as good selection of A? Yeah. A should be an irrational number. Irrational, not rational. If you get a rational number, then the performance will be bad. Okay? The performance will be very bad. Yeah. Yeah. For example, yeah, suppose your A, yeah, here I just use a simple example, 3/5. If A equals 3/5, then if your K is a multiple of 5, you get an integer. Integer mod 1, 0, right? Integer when you mod 1, it's 0. Yeah. So then you have many keys, you will map it to the 0 slot. That's very bad, right? So you don't want that happen, okay? So you want the irrational number. So you know what's the irrational number, right? Yeah. Yeah. Irrational number, you cannot represent as a fraction, as an integer, numerator, denominator, integer type fraction. Yeah. So let's say P over Q. Yeah. Okay. So irrational number, yeah. So this is the rational number. Okay. Any rational number can be represented as P over Q, with P and Q are integers. Yeah, Q cannot be 0. Yeah. Q non-zero integers, P, Q. Yeah. Any rational number can be represented as that fractions, this kind of fractions. Yeah. But irrational, you cannot. You cannot represent in this way. Yeah. All right. For example, golden ratio is irrational. Yeah. So, with this golden ratio, that's a good candidate for our capital A, but we need to drop that 1. Yeah. That 1. Yeah. We only take the fractional part. Yeah. So when we use the golden ratio, okay? All right. Yeah. A perfect hash function here. We want to do, what's the perfect hash function? Actually, a perfect hash function does not exist. Nobody can find a perfect hash function, okay? Yeah. But here we just describe a perfect hash function. What is a perfect hash function? Always map 2 keys to 2 different slots. Always map 2 different keys to 2 different slots. That's for a perfect hash function. But you can never make it. Yeah. So there is no perfect hash function. Yeah. Any hash function, any way, so people can try very hard, you make a hash function, then you need to consider the situations. 2 different keys could be mapped to the same slot. That could happen, okay? So if that happens, we get a collision problem. Yeah. 2 hash keys are mapped to the same slot, so it's a collision problem. So our next step, we need to solve if a collision problem occurs, what should we do? We need to find a solution. Solving the collision problem. Then, so you can use your hash table data structure in the real world applications. Yeah, because you need to deal with the collision problem. Okay, all right. 2 keys are hashed to the same slot. Yeah. Conclusion, no hash function can avoid the collision problem. Yeah. But if the percentage of the collision occur, if too high, then your hash algorithm will be very slow. Very slow. If the collision occurs the percentage too high, collision rate is too high, then the overall performance would be very slow. So you want to make that collision problem rate very low. Okay, all right. Resolving collision. So here, some simple strategy. So here the first one, chaining method. Chaining simple, but may not be very good. Chaining. Chaining, we use linked list. How do you create a chaining? When a collision occurs, we use a linked list to store all those elements that are mapped to the same slot. So for each slot we associate with, so here, each slot we associate with the linked list. Okay, so one linked list for each slot. If you have multiple elements hashed to the same slot, so your linked list could be quite long. The longer, then the slower the overall performance. Slower the performance. Okay, all right. So this method. So here, this method. So you can see, may not be very good. So this linked list method, may not be very good. All right. So the worst case, big O of m. So that linked list is, hold too many elements. Too many elements. So that's not acceptable. So this performance is not acceptable. Big O of 1. Okay. So we want to have big O of, close to big O of 1. Close to big O of 1. So not too long. The length of the linked list, not too long. Okay? All right. The best, we want to have big O of 1. So you can have 2, 3, just some number, but not too big. All right. Average, we also want to have big O of 1. Average. All right. So that's the chaining, resolving collision by chaining. Measure average number of elements in a chain. All right. So there is a load factor concept. Because think about this method. Actually, this method has although its overall performance may not be very good, but it has a property. You can map any number of elements into this, because your linked list can grow, right? But that's not a good thing, because the performance will be very slow, very, very slow. All right. So here, the load factor, a hash table T has M slots, But how many keys we want to map to this hash table? How many keys? Okay, So n elements. This n elements could be larger than m, right? So when you use the chaining method, so here we're talking about the chain method. So other method, we do not have the same property. Other method, the property will be different. So here, this chaining method, and so we look at the alpha equals n over m. This number could be greater than 1. We allow this number greater than 1 because chaining. We use chaining. If you have more elements, so we store in the linked lists. All right. Chaining. So less than 1, equal to 1, greater than 1. All possible. But you can see the larger the alpha, the slower the performance. Because you have too many elements in the fixed number of slots. So when you hash more and more elements, the overall performance will be slower and slower. So it's not a good method. So this method is not a good method. Yeah. All right. Yeah. Simple uniform hashing. Yeah. So uniform. So here we assume, the hash keys spread uniformly, randomly, uniformly. Yeah. All right. So any given element is equally likely to hash into any of the M slots. So that's the ideal situation. Ideal case. Yeah. Yeah. All right. Yeah. So in that one, so we can get the best performance. Yeah. Yeah. So, all right. Independently of where any other element has to hash. Yeah. Yeah. So independent, not correlated. So if some of the elements are correlated, so then the performance would be worse. Yeah. Yeah. All right. Yeah. So that average case 1 plus alpha. Yeah, 1 plus alpha. So that 1, yeah, alpha, yeah. Because first you need to go to that slot. So 1 operation. After you get to that slot, then you need to search the linked list. So the average number you need to look at in the linked list is that alpha. Okay? So 1 plus alpha. Yeah. All right. All right. Yeah. Okay, yeah. So, but that's the chaining method. Chaining method, usually, we do not treat as a good method. Okay, yeah. It's a simple, yeah, but usually not very good. Okay, all right. Because usually people want to avoid using linked list. Yeah. So we do not want to use linked list here. Okay, so now open addressing, another strategy to resolve collision problem. Open addressing. Address open, okay? Open, that means you can use any location as the address. When you resolve one element that is hashed to a slot, but that slot already occupied, then you can go to other slots, other empty slots. Yeah. But you need to follow some order to other slots. Yeah. So here, yeah. Right, so we do not use the linked list. Yeah. So now, without linked lists, so each element, each slot can only hold one element, at the most one. It could be empty, at the most one. You cannot put 2 different elements in one slot. Yeah. So usually we want to use this type of hash table. Okay? So each slot can hold no more than one element. Yeah. All right. No space outside the table is used. Now, linked list uses space outside the table, right? Yeah. That linked list. Yeah. Out of control. Yeah. Yeah. All right. And here the load factor alpha m over n should be less than equal to 1, right? Cannot be greater than 1. In this case, less than equal to 1. Yeah. And usually less than 1. Yeah. Because if equals 1, then the collision problem will be higher, right? Collision rate will be higher. Yeah. So we leave some room. Yeah. So the n number smaller than m, so we leave some room, although we waste some space, right? But we reduce the collision rate. Yeah. So that's important. We can reduce, we want to significantly reduce the collision rate. Yeah. All right. In this open addressing method, how to handle a collision. Yeah. So very simple, very straightforward idea. Find next available slot. You just look at the next slot, okay? If current slot occupied, you just look at the next one, okay? Sequential, in the sequential order, next one, available or not. Another next one, available or not. Yeah. Very simple. Yeah. All right, so, but to choose the next available slot, there are many different ways. Some simple, some more advanced. More advanced, we try to make the resolving method with better performance. All right, so here, probe sequence. So the concept, because we need to find a location. So you need to make probing, a probing process. When you search for a vacant slot, you need to do probing, okay? You need to check several locations. So that's the probing sequence. The slot at h of k is not available. So here, then you need to go to the next position to check. The next position, what is next position? You use another auxiliary function to tell you where is the next location. Another auxiliary function, okay? Yeah. So the first h function, but you need a second auxiliary function to tell you where to go, okay? And so on, yeah. Here, you just look at the next one, that's a, simplest strategy, okay? Yeah, like that. Yeah. But usually this method, not very good. Yeah. You just look at the adjacent one. Yeah, this method usually not performing well. Yeah. All right. Eventually, but this one, eventually, you can find a vacant slot. Yeah. The problem is you may need to jump too many times, right? Then it will be slower. It would be slower. All right. General formulation for the sequence of locations. Yeah. So here, so we call it, this is the, probing sequence. Yeah. Look at that, yeah. So hash, so here, our hash function, we use 2 parameters to determine the location. Yeah. The same key, but the next location we want to see. Yeah. So this is the probe sequence. Yeah. Okay, all right. Properties of a probe sequence. The sequence should cover all the slots. If you want to create a probe sequence, then your probe sequence should cover all the possible slots. Otherwise, your hash function design is not good. Yeah. Yeah. So when you design your hash function, you need to have this property. Okay, all right. Yeah. All right. So that means this probe sequence just a permutation of these m integers, consecutive integers. A permutation. Yeah. Yeah. Because it's a permutation, you cover all the slot numbers. Yeah. So you never miss any slot number. Okay? Yeah. So it's a permutation. Yeah. All right. The simplest probe sequence, yeah. The adjacent one, so that one. The same probe sequence, hash function just plus 1, 2, 3. Too simple. Yeah. So this is simplest. Yeah. Yeah. This one has the required property, yeah. But this one, you will see, its performance usually not very good. Yeah. Yeah. The performance. So we want to improve the performance. Yeah. All right. Yeah. So there is some, problem for this method. some serious problem. Yeah. So here, linear probing. So actually what we are doing is a linear, special case of the linear probing. What's the linear probing? We need an auxiliary hash function. Other than our first hash function, we need a second auxiliary hash function. Yeah. So, all right. Sorry. Oh, yeah, our hash function, so here, just h prime, but we use h prime, here we plus that I mod m, that's the linear probing. Linear probing, all right? Yeah. The main problem of the linear probing, so what's that? Main problem. There is a primary clustering problem. Clustering, okay? So you can think about, so here, if I draw the diagram here. So think about, if there is a cluster, here we treat, if these slots are occupied, so there is a cluster here, okay? It's a primary cluster, so you can see that cluster. So what's the primary cluster? Your eye can see it immediately. That's the primary cluster, okay? Your eye can see, a group of slots are all occupied to form a cluster. That's the primary cluster, okay? A cluster of occupied slots. When this happens, if a hash value hits a cluster, it needs to go through. It takes many steps to pass the cluster, right? Yeah, because you need to jump next one. So you need to, every time you look at the next available adjacent location, but it takes a while to pass a cluster, right? If your cluster is, relatively big, it takes a while, you can pass the cluster. So that performance is not good, okay? Yeah. So that's the, main problem. Yeah. All right. So we have to go through long runs of occupied slots. Yeah. So that's, for linear probing, this primary clustering problem cause the performance slow down. Okay? Yeah. How to improve it? Yeah. So to improve it, we want to jump faster, right? You want to pass that cluster faster, right? Yeah. With fewer number of jumps. Yeah. So that means your second function should be a bigger function, right? Yeah. So how about I square? Okay? I mean, just to jump faster. Okay? Jump faster. Yeah. Quadratic function. Yeah. So the linear probing, the next one, improved one, quadratic probing. We use a quadratic function. We add a quadratic function here. Okay? So we can jump faster. We pass a cluster with a fewer number of jumps. Yeah. Yeah. So you can see. Yeah. All right. Yeah. All right. Yeah. All right. But that, so here, let me just, I do not go too far, yeah, because, a lot of the discussion. So that will be too long, right? Yeah, that would be too long. Okay. So here I do not go too far. All right. Yeah. So here I only, talk about the idea. To complete the story. Complete this hashing story. Yeah. All right. How to improve here? To answer this question, how to improve it? Yeah. So yeah. First solution is we use quadratic probing. We use quadratic probing. So we define a quadratic function there. Okay? Yeah. All right. Quadratic function. Yeah. For example, ai squared plus bi. That's a quadratic function. If we define a quadratic function, then you can see when we have a collision, the next available slot, we use this function. We add this number to the h prime function. So we will jump faster, right? Yeah. So we can pass a primary cluster faster. Yeah. All right. So it looks like you can improve the overall performance in certain way. Yeah. But it has another problem. Yeah. So this solution, although improved the linear probing method, but it has its own problem. So what's that? This time, another clustering problem. So not the primary clustering, it's called a secondary clustering. Secondary clustering. Primary clustering, your eyes, you can see the cluster easily. Okay? Yeah. Because this group of slots occupy. The secondary clustering, it's not easy to see the clustering, but you will hit a or we can treat as a weaker cluster. Yeah. For example, so you have a few elements here. Then open slots, a few elements occupied there. Then open. Secondary clustering, that means, so if you hit this one, because you jump faster, but when you jump, you hit another occupied one. All right? Yeah. Then you hit another occupied one. Okay? Yeah. Although there are some distance to separate, but can you treat this one as secondary cluster? Okay? Yeah. So they're not immediate cluster. Okay? But they form a potential cluster based on that quadratic, related to that quadratic function. If you apply the quadratic function, you will hit, some indirect cluster. Okay? Indirect cluster. So we call a secondary cluster. All right. Yeah. The quadratic, we may have that one. Yeah. So it's better than the linear probing, but still, not ideal solution. At least you can say it's not ideal solution. Yeah. So here you can see how hard to design a good hash function. How hard to design a good hash function. Okay? So people try many different ways, but to resolve collision problems, still, you need to pay a lot of effort to design a, good resolving strategy. Yeah. All right. Okay. Yeah. So I just want to, give you this much background information for hashing. Yeah. All right. So then I may give you, so in the final, I may give you a few concept questions. So here we don't have the computation questions, just a few concept questions related to hashing. Yeah. So in the final, because we still, we have two parts, part A, part B. Part A, concept questions. Yeah. So, concept questions, because this part we haven't practiced. So this hashing part we haven't practiced, right? Yeah. Oh, did we practice a little bit? Oh, we practiced a little bit, right? In our Part A, homework assignment Part A. The current quiz, the quiz, not current quiz. Oh, yeah. Or we may not practice, if we haven't practiced, so then we need to practice. Yeah. Oh, we haven't practiced heap and hashing. Yeah. So we need another quiz to practice heap and hashing. Yeah. But when we do that quiz, our last quiz, that quiz is also part A of our final. 10 questions of our final. Okay. So our last quiz, the same as part A of final. Yeah. So then, another 15 questions for part B. Yeah. Problem solving questions. Yeah. Okay, all right. Yeah, because today, then we have our last class on Wednesday, right? Yeah. Last class, I plan to give you a few examples related to heap. Yeah. Because heap, we do not have a chance to practice, right? No. Because in our homework number 2 part, we couldn't practice heap questions. So in our next review class, I will give you several heap-related questions. So I show you in class. So we treat it as the practice. So then in the final, when I give you heap-related question, so you use those examples. Okay? So you use the examples we will do on Wednesday. So that's the only chance we can practice in class. Okay? So I just explain the details. Yeah, so I will give you several such questions. Yeah. 5 or 6 those such questions about the heap. Yeah. So next class. Yeah. All right. Yeah. Now I want to solve one problem. Yeah. So this one, because we did several special case before, but now we want to get a general solution. Find the second largest element in an n-element array of an n-element array. Okay, so there is a formula. Some students, I saw, some students, so they find a formula. Yeah. So when we solve our, some of the previous questions, so that is m plus seeding function of log of n. So log actually the log base 2. Log base 2 of n minus 2. That's the general formula. Okay? Yeah, so here, log base 2. This is the general formula. Yeah. Here, I want to explain how to derive this formula. Yeah. Okay? Yeah. Because the method is useful. Yeah. So then later, so in the final, I will give you a few related questions. Okay? A few related questions. So you can apply formula. After today's class, then in our final, some questions, you can, use this formula to solve the problem. Right? So you do not need to, work it out, yeah, because it takes too much time. You will plug in the formula much faster. Okay? Yeah. So this formula, yeah, you need to use. Yeah. All right. So let me explain. So here there are n elements. So here we consider these n elements: x1, x2, x3, xn. these n elements. So when we do comparisons, so we use a method I talked about before, tournament method. So we just imagine they are n players. So we want to organize a tournament, to find a, top player, second best player, top player, largest one, second best player, second largest element. Okay, so here we apply the tournament method. Tournament method. Okay? Yeah. All right. So we group them in pairs. So the tournament method typically x1, x2, the first pair, the players, x3, x4, second pair, and so on. Okay? Yeah. All right? Yeah. All right. But the last one, xn, we don't know if there is a pair or not for the last one. Because here we don't know even number or odd number, right? Yeah. So some uncertainty. Although you can do discussion when n is even or n is odd, but that could be very complicated, right? Yeah. Too many cases. Yeah. Growing. Because each round we have that even odd problem, right? Every round. So here, the first round, all the losers are eliminated. Then the next round, okay? Then pair them again. Then all the losers eliminated. So then move to so here, if one element does not have a pair, player to play, then this player moves to the next round automatically, right? Yeah. This player, idle in the current round, but moving to the next round automatically. So then we pair them again, okay? So then, we pair, If another player idling, move to the next round, okay? All right. Yeah. Yeah. So the typical tournament method, okay? Yeah. Just assuming that way. All right. So now, how many games to play to find the winner? So the champion, the final champion, the winner. So here, the first question, how many games to play? That means how many comparisons do we need to get a champion? So if we use this tournament method, okay? Yeah. How many games to play to get the final winner? Can you see that? Yeah. So although here, a lot of uncertainty, right? But can you still get the answer? How many games, total games to play in order to get the final winner, the champion of the whole tournament? Can you see that? Given n elements to find the largest one, how many comparisons? Given n elements to find the largest element. Okay, so here, another question. To find the largest element in an n-element array. How many comparisons? Yeah. the answer. We already know answer n minus 1, right? Yeah. Is it the same thing here? To get a champion, we need n minus 1 games to play. Can you see that? Yeah. Because each game eliminates one player. At the end, you eliminate n minus 1 player, right? So the winner, the final winner eliminates n minus 1 players through n minus 1 games. Yeah. Here, although the grouping is very complicated, right? Yeah. Each round, so how to group them, very complicated. Yeah. But it doesn't matter. No matter how you group, no matter how you group them, at the end, you just need n minus 1 games in order to get the final winner. Okay? Yeah. All right. All right, so let's write down. Yeah, because we need to find the champion first. You know, the best player first. Yeah. To find the best player, we need n minus 1 games. Okay? All right. But that's not our goal. Our goal, we want to find the second best. Second best. Okay? Yeah. Second largest element. So the question is, how do we find the second largest element? How do we find the second largest element? Largest, it's easy. Yeah. But now, we want to find, so here, the goal, find the second largest element. And we already find the largest under that condition. Where to look? Where to do the search for the second largest element? Okay? So, or another question I ask you, so how to determine the candidates for the second largest. Candidates. What are those candidates? Yeah, yes. Yeah. Right. All right. Yeah. So other students understand, how to determine the candidates. Candidates related to the winner, right? The candidates should have some relationship with the winner, right? Now, in order to determine the candidates, what are the relationship between the candidates and the final winner? Think about that. What's the relationship between the candidates and the final winner? That's important. That relationship. So the answer is all candidates are eliminated by the winner directly, the final winner. So if we want, not the winner of each game, okay, the final winner or the champion, final winner directly. So those players that play against the final winner directly through all rounds, yeah, because the final winner, they need to, beat certain players moving up. Those players beaten by the final winner in all the rounds, they are the candidates, right? Yes, they are the candidates. Because other candidates, when they do not have a chance against the final winner, they are beaten by these candidates, right? They beaten by candidates. Yeah. What? Yeah. Yes. Right. Because that number, the number of rounds, you need to estimate. You need to estimate the number of rounds, right? Yeah. Number of rounds. That's the seeding function of log base 2 of n. Yeah. Because some player idling, right? Yeah. So you take seeding function. Okay. N is not power of 2. And if n is power 2, it's just log base 2 of n. But some rounds idling, right? Yeah. So the number of rounds number, when you consider idling, so seeding function. Yeah. So then the number of candidates. So here the number of candidates. Seeding function of log base 2 of n. Okay? Yeah. Because you consider, idling case. Idling case, Yeah. So you take seeding function. All right? Yeah. All right. So this many candidates. Now you find the largest one among the candidates, right? So the largest one among the candidates. That's this number minus 1, but that's the, second round. But you need to add plus n minus 1 for the largest, okay? So then the total is m plus minus 2. That's the formula. That's the formula. Okay? That's how we find the second largest. Yeah. Not too hard. Yeah. Not too hard. Yeah. But the thinking. Yeah. So here, the thinking. Yeah. In order to get the answer, the thinking, it's much harder than find the largest, only the largest. But you need to find the candidates. So you need to describe the candidates. What are the candidates? Okay, yeah. Second largest. Yeah. But here, if we talk about the third largest, then much harder, because third largest, in order to find the because there is a problem is the third largest is different from second largest. Second largest, you have to find the largest first, right? Yeah. Question? Log of log? Why log of?
Because you have to be log of seeding log candidates. The second largest will have to be the third largest at least. So it should be n plus seeding of log is log 2. The seeding of log is 2 log seeding log 2.
Another log? Why you need so many log? Nested log? Yeah. That, yeah, because here you look at the number of rounds, right? You know, yeah. And right. Yeah. Yeah. So here, one easy way to see it. First, when n is power of 2, 2 to the k, how many rounds to play? So you can see. K, right? K rounds. Yeah. K rounds. Yeah. 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 So each round, one candidate, right? One candidate each round. So you get a number of candidates, K candidates, right? K candidates. So that's log base 2 of n. Yeah. But here, n is a power of 2 number. In general, it is not power of 2, okay? N is not power of 2, so you can also do the round by round, but each round you may have one player idling, okay? Not playing, moving up directly, okay? Yeah. So that factor when you considered, so when you take the, you can only do the seeding function to, yeah. Because idling, so your n, so you're moving up, okay? When you estimate number of rounds, you're moving up, okay? Yeah. All right. Yeah. So that is this case. Yeah. Yeah. So here, I make comment. So when you think about the third largest, then much more complicated. Yeah. So the main reason is this. I point out one property. So when people talk about the third largest, yeah. For us, it probably too hard. Okay. Yeah. The third largest, the problem is, when you find the second largest, you have to find the largest first, then second largest. But when you find the third largest, do you need to find the largest first? Do you need to find which one is largest first? Second largest second, then third largest? Yeah. You may not need to do that. Okay? Yeah. Think about this logic. You may not need to find which element is the largest first. Think about, if you find one that is among top 2, can you eliminate that one? Can you eliminate the element that is among top 2? But if the element among top 2, you don't know if it is largest or second largest, right? You only know one element is in top 2, you can eliminate it. Okay? Yeah? So one element is among top 2, you eliminate it. So that's why the third largest, you get a situation different from second largest. Yeah. Because second largest, you have to find the top one. Without knowing top one, how can you get a second largest? But third largest, you don't have this logic. Without knowing which one top one, which one second highest, you can still find third largest, right? Yeah. Yeah. Because just the which one, first one, second one, that is unknown. First one, second one is unknown. Other than that, the third one below those two, that's possible, right? Think about find the median of 5 elements. That one, we don't know which one largest. We don't know the second largest. But we find the third largest. Median of 5, that's third largest. That's third largest. Yeah. So here, one comment. Yeah. All right. Another conclusion I want to make related to this question. Yeah. So only, 3 or 4 minutes left. Yeah. So here, so let me give you a simple application of our previous result. Yeah. All right. Now I give you the question. All right. given 1,000 elements. Okay, array elements, yeah. Okay, so we want to find one that is not the maximum and it is not among bottom 10. Not a bottom 10. Yeah, not the maximum, not in bottom 10. What's the minimum number of comparisons we need to find this element? Not the maximum, but not bottom 10. What's the maximum? Yeah. Can you use the previous result to solve? Okay, all right. Yeah. So although here 1,000 elements, yeah. So that number is large, right? Yeah. But when we apply the formula, so here we apply the formula, n plus seeding function log base 2 of n minus 2, but here our n equals 12. Not the bottom 10, so we take 10 element at the bottom, okay, arbitrary 10 element. Not top 1, so another element, 11th, and this element, 12th, okay? So we select 12 elements from the given array, okay? Arbitrary 12, okay? Then we find the second largest of the 12, arbitrary 12, okay? So 12 plus seeding function log base 2 of 12 minus 2, okay? 10 plus seeding function 4, right? Yeah, 4. 14. 14. Okay? Can you solve a problem like this? So in the final, I may give you a question like this one. You just apply the, this formula directly. Okay? Second largest directly. Okay. 12. Okay? Yeah. Yeah. Do not plug in 1,000. Okay? If you plug in 1,000 in a second, too many. Yeah, because here we want to find the best answer. Here, this 14. 14 is the best answer. So what? Yeah, because 1,000 you use too many comparisons. Yeah.
If we use 1,000, that would be the worst case.
No, that's the very second. That's just second, right? Yeah, yeah. It is satisfy the requirement, but too many. So here the question: we want to use the minimum number of comparisons to find the solution. But now you use too many. Okay, you use more than 1,000. Too many, right? So that's not good. That's not good. Okay. Yeah. All right. Yeah. So let's finish. This class. So then our last class on Wednesday, before the final. Yeah. All right. Good. Yeah. At least smoothing. Yeah. Switch. So nothing wrong. Yeah. Yeah. No freeze this time. Yeah. But that one unexpected. So that one sometimes works. Sometimes still very bad.